Okay, so here's part 2 of ergodic theory practice final exam. So number 6, let U be a unitary operator on the Hilbert space H. Define this M sub n f equals 1 over n for the sum n equals 0 to n minus 1 of u to the n f. State and prove the mean ergodic theorem. Okay, so this is a von Neumann mean ergodic theorem problem. So the theorem states to find that M sub n f is going to, or convergence to P sub f in the norm. And here P is the orthogonal projection onto this fix of U for G such that UG equals G. We're going to decompose H equals fix of U, the direct sum of the following. And let's see what we have. Let fix view equal that kernel there. And we're going to make the following claim here. So we have these inner products, HG and UHG, the difference between them. And since U is unitary, the inner products of UH comma G and H U negative 1G are equal. And UG equals G, so U negative 1G equals G, and therefore these inner products are equivalent. Okay. Here we could say the inner product I minus UH comma G equals 0. So that here I minus U H is a subset fix U perp. We're going to take the following closures and prove reverse inclusion from here. So we're going to suppose the following. And then for every H in lowercase h and capital H, this inner product equals 0. So that V comma H minus UH, that inner product equals 0. So inner product VH equals inner product VUH. And using unitarity, inner product VUH equals U negative 1V comma H, that inner product. And therefore, this inner product equals the following inner product for all lowercase h and capital H. So V equals U negative 1V, and UV equals V. So that's that we have V belongs to fix of U. So we get the following: perp equals fix of U. And then we're going to take the orthogonal complements. Set this equal to fix of U perp. And therefore H equals that fix U. Direct sum fix U perp equals fix U direct sum of the complement. So moving along here, or some would say, I'm sorry, I minus U H bar. So that's one way of saying it. Other ways of saying it too. I'm very sorry, my voice is going. Now moving along with number 6. Okay, then for Benny, F in H, F equals G plus G, where G belongs to fix of U. We have the following for H belonging to that I minus U H bar. For G, M sub n G equals 1 over n, this entire sum. Okay. And first we want to prove H equals I minus U K. And then M sub n H equals 1 over n of the following sum. So what we could do from here is M sub n H equals 1 over n equals 0 to n minus 1 of the following. And the sum telescopes, M sub n h equals this. Since u is unitary, we get these norms set equal to each other. Therefore, that norm M sub n h is less than or equal to that norm k plus norm un u to the nk over n. That's going to equal 2 norm k over n converges to 0. And now we extend to all the following for h. I minus u h bar by density. I know some people would not like me calling that just a bar over that, but I'm doing it for sake of brevity. Given epsilon is greater than 0, choose h naught equals I minus u times k, such that this norm, the difference between h and h naught, that's less than epsilon. And since m n equals is an average of unitary operators, that m sub n norm is less than or equal to 1. So norm m sub n h is less than or equal to a norm of m sub n times h minus h naught, plus norm m sub n h naught is less than or equal to this norm h minus h naught plus norm m sub n h naught. So we get the following is less than or equal to epsilon, and since it's arbitrary epsilon, that m sub n h converges to 0. And now from there, m sub n f equals m sub n g plus m sub n h merging to g. And since g is the orthogonal projection of f onto fix of u, we say that m sub n f converges to pf. And I know I went through that rather quickly, but you have this as a reference. All right, so that's problem 6, and here's problem 7. Show that the weak mixing implies ergodicity. Weak mixing means the following. Okay. Converging to 0, take a equals b and assume a is invariant. Then mu of that t to the negative n, a intersect a equals mu of a. And we substitute here 1 over n for this sum, converging to 0. And the summand is constant. So mu of a minus mu of a squared is 0, mu of a is 0, or mu of a is 1. So we could say weak mixing implies ergodic. Okay. And the last one for number 8 here. Sorry, let me take this out. Number 8, we're going to let t be ergodic and let a satisfy u of a is greater than 0. Prove the Poincare recurrence for almost every a belongs to a, t sub n, x belongs to a for infinitely many n. So Poincare recurrence, wandering set argument, does not require invertibility. So we're going to let a be in this b script with mu of a is greater than 0. Define the set of points in a that never return to a, third time. And we get the following for our b. Our b intersects here in an intersection from n equals 1 to infinity, t to the negative n, a complement. So if x it belongs to b, then x belongs to a. However, t sub n x does not belong to a. So we're going to claim that sets b, t inverse b, t negative 2b, on and on and on, are pairwise disjoint. And we're going to suppose that x belongs to t to the negative I, b intersect t to the negative jb. With 0 is less than or equal to I is less than j. And then t to the I x belongs to b, and t to the jx belongs to b. However, t to the jx equals t to the j minus I, parentheses, t to the I x. And since t to the I x belongs to b, okay, in a, and points in b never return to a at positive times, then t to the j minus I times that t to the I x is not an a. However, that t to the jx belongs to this. So we have contradiction. I spelled that wrong, sorry. Therefore, the sets t to the nb are pairwise disjoint. And since t is measure preserving, that mu of t to the negative nb equals mu of b for n is greater than or equal to 0. So for every n, we have the following. 1 is greater than this mu of this, n equals u n t to the negative nb. And that's equal to this sum, n equals 0 to n. Mu to the t, mu of t to the negative nb equals n plus 1 mu of b. Okay, and for the rest of this, letting n go to approach infinity, we must have mu of b equals 0, so almost every point of a returns to a at least once. Upgrade this to infinitely many returns for each, for each m is greater than or equal to 0, we define b sub n as this. The set b sub n consists of points in a whose mth iterate enters the set b, meaning that after that time the orbit never returns to a. And since u of b equals 0, then t is measure preserving. We get mu of t to the negative mb equals mu of b equals 0. So mu of b sub m equals 0. The set of points in a that return only finitely many times is contained here. And if x belongs to a, returns to a only finitely many times, and after its last return time m, this point here never returns to a. So we have this, and therefore this. I'm sorry, I'm losing my voice. So the set of points in a with only finitely many returns has a measure at most here. And for almost x belongs to a, the orbit returns to a many times. Okay, for that t to the n x belongs a for infinitely many n is greater than or equal to 1. So I know I went over this rather quickly, but you have this as a reference for practice, or if you just want to do some problems for fun. And my apologies if I miscommunicated or mispronounced anything. Allergies today, voices really isn't there. My apologies. But thank you very much, and have a great day.